Okay. So let me share my screen. And before I go on with the classification, let me just go back to the Firefox and just made one comment. I essentially updated here on the Canvas website these two files. And why I updated two files? Because I mean, obviously with the second file, I updated the version with all my random CV search. So kind of as we done it. And in the first file, which I encourage everyone to go kind of and double check, which is, okay, it's relatively straightforward, but I'm not sure whether anyone have done it. There was that question in the chat about whether we need one of the columns, whether we need this feature. So average number of the bedrooms in the area vs the price. And I encourage the person who asked it just to redo the training without that column, and I've done it. So I don't know if the person who asked the question have done it. Can you respond to the chat, please? If the person is on the call. Okay, I don't see the response, but what I can tell you that yes, in fact, yes, it's really that particular feature is not very important, because if I remove it, and to remove the column what do we need to do? I just create a new xtrain where I just take that column and drop it, and I've done the same from the xtest, so that now, and we can check that, for example, I think this was xtrain or xtest of xtest, yes, so that it's now contained 4 columns. And of course, we need to recreate again the new linear regression model, do the fitting, do the prediction on the training data, do the prediction on the test data. So we can also give a look on what is the intercept term and what is the coefficients. And we see that now we have 4 coefficients. And we can check that the R squared without this feature looking exactly the same as the R squared with the feature, both on the kind of training data and on the test data. I haven't compared directly my SME and RMS, but we can compare it. But it looks like this feature is definitely not very relevant, and maybe, and yes, it could be excluded. Okay, so that was the comment about. Yes, the person is Cameron is replying that yes, he got the same R2 value. Very good, yeah. But essentially, for those who were not following our back and forth, you can now, in updated version of the tutorial, you can get that operation as well. Okay, so, and now close and out, and again on this we still don't do. So let me stop sharing and reshare. Stop sharing, and I need to share my. Okay. Okay, so now let's just go to the classification. So we've done with you a little bit of regression game, and regression was kind of very basic and very illustrative concept, and classification we're just now going to go much faster and go into the notebooks, because there is a notebook on classification, and there is 2 notebooks on unsupervised learning, or kind of like how we can use unsupervised learning, and we can think how incorporated some elements of the unsupervised learning into the regression or classification task during the tutorial. Okay, so okay, so now let's go into the classification. Okay, classification, the difference between regression and classification, and this question was already asked, that in regression, what is the output? The output is a real number. This real number could be from 0 to 1, from -1 to 1, or could be any number on the whole real axis. Yes, and in fact, you know, and the idea is that it's just a continuous number. And with the classification, you get a set of discrete numbers, which are called classes. So if you have only two numbers, you know, class 0 and class 1, or class -1 and 1, in this case, it's called binary classification. And if it's like 0, 1, 2, that could be called multi-class classification. And in this case, you have three classes, and there is no special name for three-class or classification problem, four-class, five. They're all called multi-class classification problems. Okay, so on the similar language as we had to regression problem. So what do we have? Because we're still in the supervised learning setting, we have data. So we have input vectors x, we have an output vector y, and we again want to minimize our loss function, whatever the loss function is, such that our new y's are roughly speaking the same as value which is coming out from our model f. But now the big difference is that y's are now just a set of numbers, you know, 1, 2, 3, 4, 5 till k. And in this case, it will be called k-class classification problem. Okay, so very typical, a very simple very traditional example would be that, for example, binary classification, when we have only two classes, and as I mentioned to you, these have application in many places, but for example, it's very actively used in the medical field. For example, in this case, we have a malignant or benign tumor of the ocular, just based on the photograph, or maybe it might be based on some other data on the size of the tumor, age of the person, and things like this. Here we have here on this axis, we have an age, and on this axis, we have a tumor size. And if it's benign, it's blue. If it's malignant, is red. And essentially, the task of the classification is to draw this line such, and this not necessarily need to be a line. So it could be a kind of more involved curve, which create for you decision boundary. So it means that everybody who is on this side, if we get a new point and it's on this side, it means that it's, according to this model, will be not a dangerous tumor. And if it's on this side, it will be a dangerous tumor. So this is a typical classification task. Okay, so we can use linear functions for the binary classification. And typically what is done is, again, we have our input data, we have two labels, and usually it's not 1, 2, but it's 0, 1. Or -1 and 1, it depends on the field, but 0, 1 or -1 and 1 for the binary classification is typically done. And we need to predict that, you know, class is 1 is usually how you can do it, or you can try to build a model which is saying that class is 1. So if we get this if we want to do it with a linear boundary or with linear classifier, so if this product or linear combination, if you remember from the linear regression, is positive, for example, that would mean we want to have some sort of a threshold in function. If it's positive, it's a class 1. If it's negative, it's a class 0. Okay, so, and in some space, it could be decision boundary could be drawn like this. Yeah, and in this case, we can see that, okay, this linear boundary is classifying part of the points correctly and part of the points incorrectly, obviously. Yes, because we have red points here, but there are also a few red points here and one blue point here. Okay, so the question is how we need to learn this beta. And again, as in the previous case, we need some sort of loss function. And the question is, what kind of loss function can we choose? And the problem is why we cannot choose the loss function as it was in the previous case, because in the previous case, our loss function was having like a continuous values. Yeah. So it was like we have some prediction, for example, 1, 2, and the true value is 1. So the difference of these numbers have some meaning. And we cannot here do the same game because it will be just too many jumps, because our y's are 0, 1, 2, 3, 4, whatever. But I mean, it's a discrete numbers. Okay, and what you can show that you can formulate what is called maximum, like, or you can do what is called the likelihood estimation, and you can perform kind of maximization of this likelihood, and you do what is called maximum likelihood estimation, which is essentially kind of your loss function is giving you the probability that for the given x you get a value y. So when you can do it like point by point for every data point, so we need to choose such beta. So our loss function will be given by something like this. This is one of the choices. There are other choices, but this is quite a natural choice, and there are some reasons why it's a nice choice. And in order to simplify its kind of computation with such a loss function, which is kind of a conditional probability given input x, what is the probability that the value y or the value of the output will get a given value. In order to simplify it, and why we want to a little bit simplify, because if you have here a product, and if you have a product, for example, of very small numbers, we could get very quickly 0. So if your data set is very large, so it's much better to take a log of this function. And in that case, instead of product, we get a sum. Okay, and what is usually formulated is called negative log likelihood. So it's just minus log of this likelihood function. And now we can try to play with this kind of loss function, and we also need to find the proper choice of the probability function. Okay, so, and what is the intuition behind the likelihood functions is that if we have, this is one class, this is another class, and if the likelihood function is going to draw a boundary, something like this likelihood function is a good likelihood function because it's highly likely that, it's a right solution. It looks like a right solution, but if it's something like this, it doesn't look right. Yeah, so kind of this is the kind of, if you don't know, kind of don't understand what I'm saying, likelihood, it means that, okay, it should be the probability that, when we take, if the input is this one, it should tell us that this is a red class. If we take the point here with a high probability, it should say it's a blue class. Okay, and very good probability function. And one could, start a discussion why, but I mean, let's skip it because we're trying to do it a little bit practical, is what is called logistic function or sigmoid function. And this function is looking like this. So for the negative values, and in principle, it's going from minus infinity. It's starting 0, 0, 0, 0, 0, 0. And as it's getting closer to the 0 on x-axis, it's beginning to grow. In 0, it's crossing the y-axis in the 1/2 value, and afterwards increasing till 1 in the same way, and afterwards it stays 1, 1, 1, 1, 1, 1. Okay, so, and the natural kind of it's one of the choices. It's not necessary choice, and you can choose some other functions to simulate your probability distribution, because what do you need to have for the probability? It needs to be a function which satisfy definitions of the what it is. What does it mean that something is a probability function? Yes, so kind of it means that it should be for the all possible values. If you take all possible values, it should sum up to 1. It should be positive. It should be bounded from 0 to 1, and essentially that's it. And the sigmoid is satisfying all these properties. Okay, and okay, so do I have the, okay, no. Okay, let me show how the sigmoid is looking like, because it's just an 1 over 1 minus e to the z. Okay, so let me just do this and do sigmoid. So for those of you who don't know what the sigmoid function is something like this: 1 over 1 plus e to the minus x. So when the x is large and negative, we get e to the, okay, when the x is large and negative, we get e to the minus large number. So we get e to the very large positive number. So e to the positive number is huge, and we get 1 divided by the huge number, we get 0. And when the e of x is positive, yes, and large, we get e to the minus huge number, and this is 0, and we get roughly 1. So that in extreme cases, and one can also check that, you know, when the x is equal to 0, we get e to the x is 1, or e to the 0 is 1, so we get 1/2. So essentially, that's function. This function is satisfying these criteria, and we could even, you know, for those of you who are not convinced, you can just take matplotlib and plot it in 2 lines of code. Yes, so you just need to take an x from -6 to 6, as in this example, split it into the 20 or 30 pieces, and plot this function. I encourage you to do it as a little practice. Okay, so let's go back to the slides. Okay, and so now our kind of this is also this model. If we don't do anything with value which we obtain afterwards of this sigmoid, because what this function will spit out, this probability function, it will spit out a number from 0 to 1, and you could see that this is a model of regression, in fact, which is called logistic regression. But as I mentioned to you, kind of already in answering of one of the questions, that, you know, this kind of regression model, which is defined kind of the output from 0 to 1, could be very easily converted to the classifier by adding one more step, which is saying that, okay, if the output of regression model is above 1/2, that would be 1, and if it's below 1/2, that would be 0. So it's very easy kind of to implement such kind of transition from this sort of regression models into the classification model. Okay, so yes, I mean, the first, there is this couple of things which we've seen, this mathematical relationship between the sigmoid functions. Okay, first of all, this is our kind of probability. Yes, and we're saying that, so we're kind of optimizing our model, so we're choosing betas as such that if sigmoid is the probability of the probability to have to given x corresponds to class 1 is given by the sigmoid, the probability for given x to have class 0 is going 1 minus probability, yes, because the probability should conserve. And this is transferred to the classification by a very simple thing. We just add threshold, yes. So if the probability in being class 1 is greater than 1/2, we are in the class 1. If the probability being in class 1/2 is smaller than 1/2, it means that we're in the class 0. So essentially, and that's how any even multi-class classification problems will work. Okay. And this could be even simplified because of the properties of the sigmoid, that if the argument of the sigmoid take into account that sigmoid is equal to 1/2 in the x is equal to 0. So if the sigmoid, or kind of if the argument of the sigmoid is positive, it means that you are somewhere here. It means that you are definitely greater than 1/2. So you can really see it as, okay, if this is positive, it means that you're in a class 1 because you are here with respect to the probability function. And if you are negative, if this inner product or this kind of sum is negative, you are on this part, and it means that you are in the class 0. And this is very simple relations which show us, you know, connection to the linear classifiers of very simple, you know, classification task. How you do multi-class classification? Multi-class classification, you need to choose again probability. You need to choose the probability function that you're in a class 1 or in a class 2 or in a class 3 and so on. Yes, and obviously, you know, the multi-class classification problems are important in many domains, as it's stated here. You know, disease diagnosis, object classifications, and things like this. And essentially, what you need to do now, you need to draw several decision boundaries to separate your classes in some X's in some multi-dimensional space. Yeah. And how you do it? You do it like this. So because we've seen now that logistic regression function or sigmoid function works very, very well. So now what we have for the multi-class classification, we're going to have not one set of betas, but the multiple sets of betas. For every class, there will be each own set of beta. Yes. And how it works, that we're saying that probability of being in a given class is proportional to its own exponential. And in that case, in order to say that now we're normalized on 1, because probability is supposed to be normalized on 1, this means that the probability to be in one class, given class y, is just given by exponential on the sum of all the rest exponentials. And this is always positive. This quantity is from 0 to 1. And if you sum over the all classes, it means that you're summing all over the fractions like this, you get 1. So it's a wonderful and simple probability function. And the function which is doing this job, so kind of have an input kz's, and doing kind of forming this probability is in a standard way is called softmax. And those of you who have seen a little bit of, I don't know, TensorFlow Keras on the, for example, MNIST dataset, the dataset of handwritten digits, that will be the last layer because you need to classify 10 possible digits from 0 to 9. That will be the softmax, and you assign the class to the maximum probability. So you're saying, okay, you're forming the list of the k numbers, which are all positive and sum up to 1, and that one which is the biggest of them, that will correspond to the given class. Okay. But again, you can also treat it as a softmax, as a regression task, because if you don't do the thresholding and you're saying, okay, maximum of this list will be given to the class, you can treat it as a regression. So you see, it's kind of, if you know how to solve regression problems, it's usually very easy and straightforward to reform them into the classification problems. Okay. So, and just a little bit step back, if we want to see it as a regression, in that case, we just don't need to do the class assignment in the end. We just can do the optimization over the all parameters to find which kind of what is the value we're having. Okay, and it's optimized using our negative log likelihood. We can still do it, yeah, and we can simultaneously update all the parameters. Okay, so, and now the kind of the last bit of the kind of formal lecture before we go to the IPython notebook, how we are going to evaluate how good or how bad is our classification task. And there are several approaches how you can do it, but one which is very useful and very important, and kind of it's useful to understand because we hear these words on TV which are related, I don't know, to some medical issues or efficiency of vaccines and things like this. So we can, if we're talking about classification problem, we can have 4 possible events which are coming out. We can have a true positive, which means that events is positive and predicted positive. Yes, kind of is a kind of you guess the right class, your model is predicted the right class, and it's belong to the right class. Yes, kind of false negative. It means that you have one class. For example, in binary case, you have a class 0, but your model is predicted at class 1. True negative, again, it means that it's negative class and predicted negative, and the false positive is it's actually negative but predicted positive. So kind of like a 4x4 matrix, and you can express. There is a term which is called accuracy, and what is accuracy is a true positive plus true negative divided by the number of data points, and the error, of course, is false positive and the false negative, because that's both errors divided by the number of points which you are classifying. Okay. So, and what we will see in some of the examples, that our system is going to give us what is called confusion matrix, which is saying that, okay, so as a predicted class is correct, and the actual class, yes, true positive, true negative, false negative, and false positive. And where we are coming into the kind of more everyday literature, or sometimes to the medical literature with this, for example, with this nomenclature, is with there is 2 notions which are very often used and which you can hear, which is a sensitivity and specificity. So what is sensitivity? Sensitivity is ratio of the true positive on true positive plus false negative. So who are false negative are those who are actually positive but predicted negative. Yes, and you want your sensitivity to be very, very high. So if you want, yes, kind of you want the false negative to be minimal, but I mean, these two quantities are saying slightly different story, and sometimes it's important to understand what the story these quantities are saying, because you could very often hear, and for example, we've heard in the contents of COVID that, oh, this test had this sensitivity and this specificity, or this vaccine had this sensitivity and this specificity, or it's only telling you sensitivity but not specificity, and so on and so forth. Okay, so, and specificity is true negative on true negative plus false positive. So, and if we'll consider an example like whether you get a diagnosis of some disease, yeah. So what the sensitivity of the test is telling you, yes, kind of like the sensitivity is telling you that if you have a disease, what is the probability, what is the probability that you really have it? Yes, kind of, because if we're saying that it's true positive, yes, you have it, true negative, you don't have it. So do you really have it? So that will give the probability, do you really have it? And the specificity will tell you that, do you really don't have it? What is the probability that, okay, you can interpret it as a probability, what is the probability that you really don't have a disease? So in principle, you want these both numbers to be as close to 1 as possible, or as close to 100% as possible. But sometimes it's very important to know the difference. And sometimes, as a function of the problem, you might choose when you train your model so that you might have a very high sensitivity, but you don't care about specificity, or vice versa. For example, currently machine learning is very actively used for classification of the certain astronomical objects. Yeah, kind of like there are some photographs from the sky surveys, and for example, there are problems of identifying certain objects. You can train your neural network, for example, because in that case it's neural networks to detect certain objects. And in principle, what you wanted to know, you don't mind to have a little kind of, and your problem is kind of to find, for example, all the what is called, for example, gravitational lenses or something like this. So, and you don't mind that sometimes your program is doing a mistake, because afterwards anyway it's going to be kind of voted by humans, but not that the humans will need to kind of look through the full picture of the sky, which is a huge images. But what you want your problem, or but you want your algorithm not to miss any gravitational lenses. So in this case, what you want specificity to be very high, but you don't want, and sensitivity could be a little bit lowish. So, okay, if there is a false negative, it's okay. You don't want it. I mean, you're happy to having this, I don't know, 60% or 70%, but here you want like as close to 100% as possible, because you don't want miss the astronomical object. Okay, so this is kind of non-medical example of where this is also possible. And are there any questions around this? When doing classification, there is a gap between the classes. How do you select the right position on the boundary? I'm not sure. Okay, when doing this, there is a big gap between the classes. Okay, so what do you do? In that case, you do, and this is very nicely done in the framework of something which is called support vector machines. So what you do essentially, you choose the lines which are maximally separate the boundary and draw the boundary just in between, essentially. And that distances, and we are going to give a look into the support vector classifier just now, is exactly kind of, so you push your boundary in between, and you want those vectors to be as long as high as possible, and you just put it in between. Because in principle, you don't have information where the boundary is if your classes are far away from each other. And in that case, the best is just take it in the middle, but also satisfying a couple of extra conditions, which we are going now to give a look at. Okay, so in that case, let's go into the into the Firefox, and in that case, let's try it from support vector machine. Let's click the Wikipedia article and let's have a nice image. I hope, yeah. Okay, so this is exactly the situation which you have. So you have one class here, one class there. And the question is how to draw a boundary between this and that class. How to decide, if the green is here or if the blue is here, who will be here. So what you do, you are trying to draw draw these kind of two lines, which are kind of on the boundary such that they are as far from each other as possible. So that will fix your distance. And in between, you draw a boundary, and the vector which is going from the boundary to the kind of first representative of the class on this side and on that class is called support vector. And that's why this method is called support vector machines. But essentially, you just trying to find two lines which is as far away from each other, which are parallel lines, and draw the boundary in between. Or you can formulate it vice versa. You draw a line in such a way so that you are equally far away from the closest representative of the opposite classes. Okay, I hope I answered that question. How do you determine true positive and false positive test and training split? So you can only estimate it, but you do the test and training split. You do the training on the training data, and afterwards on the test data, you do the true positive and false positive. Because in your test data, you have the answers. Okay? Okay, now let's go into the support vector machine classifier, and we're going to do it in a little medical setting. It's a very famous data set, which is a breast cancer data set. And let's start. Okay, so we want to upload standard stuff. Yes, pandas, numpy, matplotlib, seaborn. Okay, and this is so standard data set that it's even included into the list of the scikit-learn data sets. And we can load it. And by the way, what we can also do, just to demonstrate it to you. Okay, I said, yes, okay, I don't have it like that, because I just want to show you what are the other data sets which are here, but in that case, let's do it. So in this case, it's, the problem of the training for the machine learning make it even easier. Scikit-learn, why I don't want toy data set, I want just a list of data sets. Okay, yeah, so there is this data sets which are kind of quite standard. Yes, there is an iris data set which we are going to play with a little bit later, and that's a data set which is related to the iris flowers. Diabetics, digits, it's 100 in digits. Wine data set, which we've seen already. And what is a liner UD? Okay, that's some data set for the physical exercises, and the breast cancer data set which we are going to use. Okay. Okay, so now let's give a look what we've got. So we can, first of all, we can check what are the description keys of these data sets. So we have data, because it's these data sets are organized as dictionaries. So we have data, target, so what do we want to predict? We have some description, which is very interesting, some features names, and the data module. Okay, so, and before, we can always look into the description, because, and you see, that's a nice thing, that's why you want to work with these data sets, because at least you know what you are getting into. You can read and understand and appreciate it and so on. So yeah, so this is a data set. So there is a list of attributes. So it contains 569 instances, and it's 30 features. Yes, which include different parameters of the tumors. Okay. And this is kind of summary statistics of the parameters which we get in. And out of those all entrances, 200, roughly speaking, 200 are malignant and 350 are benign. Okay, and there is a creator of this data set, and so on and so forth. Okay, so now we can start to come in doing a little bit of data science with it. Okay, so we can first of all get all the feature names, and because the object cancer is the dictionary, but we can, using the key data, we can get all the data, and afterwards give a look on what we have in our data frame. Okay, so we get all our features, 30 features, and what we could see that first of all, they are all 569 each of them, and they are all not null, which is good. It means that the data set is full. There is no missing values. Okay, we can do standard thing describe, and we can give a look. Yes, what is the mean, standard deviation, and so on and so forth. We can also check, which is not for this data set, but for some other data sets which might have a data issues problem, you can do always, if you can do comment like this. So you are just counting objects which are now in this data set. So you are counting missing values. And as you see, we have 0 missing values. Otherwise, it will be just an integer, yeah, because what this will do, what this comment will do is now, and data frame, your kind of this data frame, it's going to just replace the kind of, it's going to give back a data frame or table, which is going to have 0 if it's not null, and 1 if it's null. So if it's a missing value. And afterwards, we just do sum, which is just summing them up, and we get our answer. Yes, and I think this internal sum is summing along the one axis, and afterwards NumPy is summing along the other axis. Okay, so now we can give a look on the target. So this is our target. Yes, 0 is the one class, and that 9, and the 1 is malignant. Okay, so now we can add the kind of answer data to our data frame as the last column. Yeah, and now we can do a little bit what is called exploratory data analysis, or we can just see how the data is looking like. Okay. Sorry, I still see that my computer is showing the, okay, no, okay, so you can see my Firefox screen, yeah? Okay, good. No, because the presentation was still in a full mode, and I was thinking that maybe I'm still showing you the presentation. Okay, so now what do we do? So first, what we can give a look, we already know that the benign and malignant is 200 and 350, but we can just visualize it. Yeah, so we can this is just a little bit of fanciness, so we can do the Seaborn. So, and you see, you can set up different style for the different color patterns, and the style of the graph and the color patterns. And it's very easy because it's just, what does it do? It's do the counting number of zeros and number of ones and plot to you a little bar. Okay, so now we can do a little bit more fancy. So now we can go through the every column and just plot this with this graph. You see, you get a list of columns, and now you just go through each column, and you can plot the distribution of the values there, which are called box plot. Yeah, so we see every feature is on this side, and here is distribution for the okay, so 0 is the cancer, 1 is no cancer. So for the cancer and non-cancerous event. Okay, so, and what box plot is showing to you, have you been told in the NumPy part or in the pandas part? Have you seen box plots before? Okay, somebody have seen it? Okay, okay, so Okay, so we get, okay, cool. Okay. But in that case, let's do the quick one. What is the box plot? And again, is like the best way of doing it is just do it like this. And I hope this is the right box plots. Okay, so this is our box plot. Yeah. So the straight line in the middle is the median. Yeah. So this is the median value of this feature, and this is the median value of that feature. Or kind of for the non-cancerous case for this feature, mean radius of the tumor, median of that is this one for the cancerous case, and for the mean radius of the tumor for the non-cancerous case is like this. Okay, and I hope you all know the difference between the median and mean. Okay. And now let's go to the, okay, so now what is the width? The width in distribution is the first quartile and the third quartile. Yeah. So this is from the first quartile to the third quartile. So this is like two central parts of your distribution are hidden here. So it means that this is your kind of most of the data. And what is the sticks are sticking out? It's a maximum and minimum. So it's a from the boundaries of the first quartile, you just shift in this direction, and you're shifting in this direction on what is called IQR. And what is the IQR? For people who have seen the box plots. Okay, I see. And if the dots outside is outliers. Okay, and I suggest that you identify whose IQRs. So we can say that, okay, so this is our minimum, this is maximum, and this is outliers. And interestingly enough, and this was told already, that, you know, if these distances are different, it tells that, you know, the distribution is not symmetric. And so it means that, okay, in the cancerous case, it's not symmetric, and you see kind of the tail here is a little bit more so kind of like for the cancerous cases, you can definitely say that, you know, okay, you have a tendency towards larger tumor sizes, at least on this data set. And yes, kind of while for the kind of non-cancerous case, it's more symmetric. Okay. So when you can do the similar analysis for all the rest inputs. Okay. So now there is one more interesting observation. Speaking of the classification problem, that you know, one and the same feature is not or kind of one of the same properties of one and the same of the, but you can also see it from here that, you know, the fact that we have a overlap between the values here and values here, it means that, you know, mean symmetry might be the same for the both cases, and that's doesn't really kind of answer, kind of doesn't give us the answer. And you can only make a judgment or decision based on, you know, the composition of the factors, so kind of by the several factors. But this could be seen, for example, by doing the plots like this, where you plot for example, yes, in cancer or not, so kind of all the mean areas for the non-cancerous case and the mean areas for the cancerous case, and you see kind of mean area is have an overlap. So in here is the mean smoothness is also have a huge areas of overlap. Yes, so kind of you have the same mean smoothness, whatever it is, but you cannot judge whether it's cancerous case or not. Okay. So it means that, I mean, it's a very interesting case from that point of view, when you kind of, one feature could not tell you all the story, or there is no direct correlation, kind of very simple correlation, but that we can also study with the correlation matrices. Okay. So now let's do the tame trace split. And for that, we need to take away the results of the classification outside of our data set. Yeah, and we can check it. Good. So it's only features. And the target will be only the column whether with a cancer or not cancer, because that's what we want to predict. So this is our input data. That's what we want to predict. Now we need to do the split. Yeah. Train, test, and 30% to the test, and 70% to the train. So let's do the training. And okay, and we can check that how it looks like. Okay. So now, now we finally come to the part which might be a little bit new to you, because now we need to train the classifier, but because it's written, all of that is written in with a very high degree of similarity. Okay, yes, we get the IQR is the difference between the Q3 and Q1. Very good. Interquantile range. Okay. Very good. Okay, so let's go. So we just importing this classifier, and there are many classifiers. So kind of we can use a logistic classifier, we can use SVM classifier, we can use the random forest classifier. So everything essentially what was a regression is also could be in a classifier option. We create a model and we fit the model, and that's all. It's as simple as that. And the really difficult task is optimizing the parameters and hyperparameters, because now we can just do a prediction, and in order to see what is the result, we can do the confusion metrics, or we can do some other metrics. Yeah, and oops, that's what we're getting our confusion matrix. So we get the true positive, true negative. So here will be false negative, and here will be false positive. Yeah. So, and based on this, we can now calculate with you the specificity and what was that? Specificity and sorry, what was that? Sensitivity and specificity of our classifier for this particular problem. But now what I suggest that we do, because, you know, kind of okay, the question is, can we do better with what we have? And as in the previous cases, it's a very nice thing just to do a grid search immediately and try to identify what are the parameters are. And okay, so let me explain to you what is that, what is the kernel. And for that, let me go back to I closed already. What? Yes, support vector machines. Did they have some image? Okay. Okay, so I want to just to make you a comment about the kernel, because what is the kernel? Or that's also a feature, and there are a set of standard features for the support vector machines. So because if we just put an X here, kind of like we do it with what is called a linear kernel, or we do it with the way how it's drawn here. If this is the actual points of your data set, you get essentially a linear classifier, because your data kind of there will be a linear dependence. But now we can use that idea, which I mentioned to you in the morning lecture about the features. And what we can do, in fact, we can transform the input points in some way. And there is 3 default supported the kernels. And let me see if they're here. Yes. Okay. So of course there is a linear kernel, which we understand. There is interesting polynomial kernel. So we can specify kind of the polynomial of which degree we want. And there is also quite famous RBF kernel, which is radial based function kernel, which is just exponential of minus distance between the points. And this kernel is quite popular because what does it do? It's essentially making kind of when you transfer your features using the radial based functions, what you are doing, you kind of, if your points far away, they remain kind of the kernel will be very small, and if they're getting closer, they kind of the kernel becomes larger. So it's making this transformation, so kind of to the special distance measures essentially, and kind of they're all doing this job, because this, what is the linear? It's just the inner product with which you can measure the distance. What is the polynomial? This is another way of measuring the distance, but this is quite famous and it works relatively well in many other cases. And the and also what is very nice, what the scikit-learn supporting, it's supporting your own design kernel. So you can design your own kernel for some other purposes. And for example, that is typically is done in the field of the what is called quantum machine learning with the quantum kernels. So you can design a quantum kernel which you execute, for example, on the quantum computer, and afterwards you're putting it into the classical support vector machine for pre-processing. But we're not talking about that today, but just as an idea, so that is very useful. But if you need to specify kernel, that's how you do it. Okay, but let's go back to our code. So our parameters for optimization is we're optimizing parameter C and parameter gamma, and kernel we are not optimizing, we just it's fixed. Okay, so what is parameter C? Okay, done. So where is no spot vector machine? No, where is okay? Because gamma is exactly the power of the exponential in the radial base function, but the parameter C is probably regularization coefficient. But let's see if I'm right. I want no. Why I cannot go into the list of property? Okay, let me try like this. Yes, that's what I want. So C is the regularization parameter. Okay, so because it's and this is exactly L2 regularization. Okay, so now we know what we're dealing with. So we have a very small C, kind of largest C, and very large C, and we have several powers to the exponential. Yep. And let's now do it. Okay, and now we can, okay, let's see. How long does it take? It's not that long. Okay, we can get the best parameters. So we get our regularization, the value of the gamma, and we can get our best estimator. Okay, so we can do the prediction and we can do confusion metrics, and we could see, are we doing better or are we doing worse? Okay, so here we're doing a little bit better. Oops. Yeah. Yes, overall, I think, oh no, here 102. And here, oh, here is 101. There was 101 and 102. Okay, so we improved in one and make a little bit worse in other. So, but this decrease. So overall, it helps a little bit. And yeah, we can do more search and trying to see whether we are getting better results. Okay, and in fact, we are not getting much better results here by trying to look for the more C's, or kind of the trying to look for the more values of gamma. And one could try to think about, playing with not a radial base function kernel, but also with some other kernels. Okay, so do we have any questions about this part? Okay, so I don't see any questions. And let's maybe quickly go into the unsupervised learning. And let's quickly give a look into here, because so far we were dealing you with the situation that I give you input and I give you the answer. Yes. So kind of, and that was a code supervised scenario. And now what we want to look into is that there is no answer. We don't know the answer. But the idea is that we want to find some hidden structures in the data. And this could be, in fact, a very useful tool to come together with your supervised learning scenario, because that's a way how you can create new features in your data, or you can use it for the solving your machine learning problem completely. And the very basic idea, and let me just go quickly through this, is called principal component analysis. It's very simple, or it is also called dimensionality reduction technique. And let's assume that your data is looking like this, yeah? So kind of you draw it and it's looking like this. And you can say that mostly all the difference changing in your data is explained if you move along this axis, not along this axis or this axis, but if you move along here, and a little bit more precision is achieved by that. And the principal component analysis is exactly allow you to kind of to get the components, which are called the principal components, which explain the most of the properties of the data. And then mathematically it's done with a technique which is called singular value decomposition. And for those of you who don't know what it is, you can take any matrix, not necessarily quadratic, but also rectangular, and do a singular value decomposition. What you get, you are getting in the middle, you are getting metrics which have on the diagonal eigenvalues. And here and there you get two unitaries. And if your matrix is rectangular, the dimension of the unitaries or the dimension of your central matrix will be such so that you compensate for rectangularities. And the principal components are those largest eigenvalues. You can, of course, take all, but you can say that, okay, if you have eigenvalue, I don't know, 5, 5, and afterwards 0, 0,1, 0, 0,1, 0, 0,1, you can say that these two eigenvalues, which are 5, are much greater than 0, 0,1, and you can just drop them up, or drop them away. And this is the way how you can organize kind of that's how it works. It's a linear technique for the transforming of the data, but it's extremely efficient in many situations. And what we're going to do now, we're going to do it for the very quickly for the what is called the iris data set. We can, load all the standard things. Yes, NumPy, scikit, and we have our plotting capabilities. So we can load the iris dataset, and the iris dataset is a standard dataset which is used for the classification. Kind of, it's have 3 classes because there is a three types of three types of characteristics, and that's how the data is looking like. So it's these guys, and that guys in 3D, and that's a kind of just characteristic of the iris flowers. Okay, and what we can do the PCA analysis of this. So we can, instead of working with the system in 3D, we can push it down in 2D. And how we can do it? First, let's first do some naive classification. So we can do just pick decision tree classifier, do the splitting of the data, and afterwards apply the classifier. And now what we can do otherwise, kind of, we can do the PCA decomposition. We can say that we want to flatten it into the 2D from the 3D. And we are just fitting the PCA and transforming our data. And now, instead of 3D, we have a new coordinates, which are kind of some linear combination of these coordinates, such that it's looking like this. And in some way, it's looked that it's a little bit better because this class is clearly here, but there is still a little bit of difficulty of distinguishing between these two classes. Or if we draw a line, it wouldn't be perfect, but we can do the training and we'll get a little bit higher accuracy, not spectacular, but a little bit higher. And the secret is that you need to do this transformation or dimensionality reduction in a nonlinear fashion. Okay, so we can do that. And what we can do as well, we can afterwards see, how much the component along this axis, for example, or along this axis is explaining to us the difference between the data. And this is called explain variance in the data. And now what we can do, we can just say that the first component explain 92% of initial variance. So what does it mean? It means that the first component, or moving along this axis, is explaining to us 92% of everything about this data set. And this is rather clear, yes, because if the first component is below this value, is this class, and roughly here, if between here and here is this class and here is this class. So you could in principle already see how it will work. If you include the second component, you get extra 5% of variance. Okay, so but this is, and you might ask, oh, why do you want to do something like this? Because if your data set is, several thousand dimensional, and you can suddenly see that, you can explain most of the trickiness of your data by boiling into the 3, 4, 10 dimensions out of the 10,000. This is a pretty big achievement because you already could interpret what you've got. Okay, so, and the next data set, because I'm not sure that Rene came, and what is the reason? When are we supposed to? Okay, so sorry, Rene, how much time do I have?
Ilya, you're welcome to finish whatever you need to do. It's okay.
Okay.
We'll wait with the closing. So take your time, please.
Okay, thank you. Okay, so let's load the digits data set. And let's see what it is. And this is very famous data set, another one. But usually it's mentioned in the content of the neural networks because they're particularly good in solving this problem. But you can also analyze it with kind of the other ways. So we can get, again, it's standardly kind of encoded into this in the data set of the scikit-learn. So when we can load some random digits, and that's how they look like. And this is also already, how to say, it's already scaled down version, because the original version is not 8 by 8 matrices, but it's 28 by 28, and it looks much better in all possible, kind of online tutorials. You will find it in the better version, but for our purposes, this one is good enough. Because what does it mean? It means that we have a 64 dimensions. And the question is, can we reduce these 64 dimensions? Because if this is input, it means that we have an input 64 numbers, yeah, which means, I don't know, the black will mean 1, the white means 0, and gray is somewhere between 0 and 1 on the gray scale, yeah. So, but we have an input 64 dimension, and the question is, can we do it? Let's try to do it with PCA with 2 components. And if we try to project it on 2 components with PCA, all the different classes of the numbers, we get a mess, yeah, literally, yes. So because it's, there is no way that we can, separate one blob from the other, if there was no color. And what you can do in this case, and what exists, because as I mentioned to you, that PCA is the simplest possible thing, but you can do this transformation in nonlinear. And typical example is what is called stochastic nonlinear embedding. And it's here, and let's do it for the same data. Okay, and you see, the result is not unique. It will change as the function of your random seed, but you can clearly see that even if we take away the color, we could see that there is clusters, yes. And if we look on the classes, we'll suddenly see that, okay, that corresponds to the images of the different color of the different digits. So using this unsupervised approach, because what digit it is not participated anyway in forming this projection, we could easily get some clustering. Okay, and now we can also play the same game with the explained variance. We can ask how much of the diversity in data, how many components do we need to take to explain all the diversity of data? And this is called explain variance ratio. And we can do the, for example, using the PCA, and we can do it, and we can see that in our data, in all our because our problem was here that we try to project it into the 2 planes. And the question, okay, can we project it into more planes and see how much information is relevant? And that's what we can do here. So we just feed PCA, and now what we're doing in this little snippet, we're just trying to see how much of the diversity in data is explained. And as you can see that out of our 64 features, we can throw away 2/3 of features, which is not bad for the linear transformation to explain 90% of the variance of the data. Yes, so kind of like if you need to do it like on the large scale, using the even PCA and not talking about, using the a little bit more fancy nonlinear tools, we can really reduce the dimensionality of data, which becomes very important. Okay, so now 2 words about another unsupervised approach, which is called clustering. And there are examples of some clustering which can be produced by the scikit-learn. And the very typical and prototypical, when you were talking about clustering, that's what the people are talking about usually, while there are other clustering methods, but this is the most simple and straightforward one, which is called k-means. And what does it do? It's you need to say to your algorithm, but we're also going to see just now how you can estimate whether the number of clusters is wrong or right. You can say, okay, this is my data, identify 5 clusters there. Okay, so you choose the number of clusters, and afterwards the algorithm will identify the 5 given clusters, and kind of you do it, and you can see, is it good or is it bad, and so on and so forth. And kind of as a simple example, let's consider something like that. And it's essentially, what does it do? What this code is doing, we're saying that, okay, let's consider in 2 dimensions 150 points, and first 50 points are going to be centered, will come from the random Gaussian distribution, which will come in from this location, from 0, 0. Yeah, 50 random points. Afterwards, we're going to have 50 points, which we're going to label from number 50 to 100 in this data set. They will come from the point 2 minus 1. Yes, so it's here. And another one will come from here. So, and obviously, we as the humans could easily see that, okay, this is one group, this is another group, this is one more group. But the question is how to design an algorithm so that machine can do it. And so what you can do, you can design an algorithm using the facts of so there are various ways how to approach it. And kind of the straightforward and naive one is you choose randomly, because we ask, okay, identify 3 clusters. We choose randomly 3 points. Randomly, it doesn't matter. There could be only 1 cluster because we don't know the structure, because we know the structure now because we draw it and because we invent this data set. But for some arbitrary data set, we choose random 3 points, and afterwards measuring the distance from these 3 points to all the rest points. Yes, and afterwards what we're trying to do, we're trying to say that, okay, so we want to identify, we want to change these points to another 3 points such that the distance to the given point will be, which is our kind of randomly chosen point, is there will be bulk of points with respect to this point. And essentially what we can do it using the kind of relatively straightforward code, which we can check, or we can do it, we can say, okay, we don't care about the code, or we can run it, but we can use it using the okay, so this is this code, but we can also do it with the help of SciPy method, or not SciPy, but scikit-learn method. Okay, so we can do it, and it's definitely kind of telling us how it's identifying clusters and how it's choosing randomly centroids, and afterwards it's identified the centroids correctly with the clusters. And if we want to do the same with the SciPy, we need to do KNN, and we don't need to implement it manually because no, we don't want the KNN in computer. Okay, I think I have it here. Yeah, it's called k-means. Sorry. So we can do it using this procedure. Okay, but now the question is there is one more bit of input information which is absolutely not obvious, which is how many clusters. I mean, here we know that we have the 3 clusters, but imagine that you have a very multidimensional data and you could not identify by staring at it that you have 3, 4, 5 of 20 clusters. So what you can do, you can choose some measures which will help you. Okay, here is a k-means that which will help you to identify by the behavior of the certain typical distances, or the ratio of the distances between the kind of centroids and the clusters in the following way. So we can do the, again, k-means, and now we can, for our data where we know the answer is 3, yeah, kind of we can say that, but okay, let's try to identify from 1 to 8 clusters. Let's try to identify all the clusters, and now we can plot this measure, which is this ratio, and it's going to look like this. So if you, by adding new clusters, you see that this quantity is decreasing fast, it means that, okay, adding new cluster is useful. But in the moment when you see that we're not getting too much information by adding new clusters, it means that, okay, we can really stop here, and that's what we see. Because of course, you know, if we ask for clusters, we can probably, you know, separate a little bit here, or kind of separate here and here, but it's already not bringing any more new information, and that gives us a little kind of at least intuition behind how many clusters do we need more, because it's really not obvious. Okay, and how you can use it, how you can use all of it. So what you can do, so there are several ways. I mean, first of all, this is already for you classification task. So you have your input data, even if you don't know labels. This is the classes for your classification data, as it was in the TSME case. So kind of you can do, using these unsupervised methods, you can do classification. But also what you can do, you can use, like in this case, you can use these extra parameters, which is kind of the PCA components of your data, as the extra points or as the extra features to your data. And in that case, you know, if they can explain a lot of variance in the data or a lot of diversity in the data, they will be very good for identifying, and you can afterwards, you know, after adding these 2 PCA components to your data, you can use that for the some linear function. Okay. What is the difference between linear regression and Bayesian linear regression? And also, what is the goal of autoencoder? Okay, so linear regression and Bayesian linear regression are slightly different models, because the Bayesian, I mean, and there are all this field of the Bayesian estimators, and for example, kind of it's very straightforward concept which is used, for example, for the spam filters, because kind of like you're doing some hypothesis with respect whether your, I don't know, your data is satisfying certain distribution, and afterwards you update this distribution. In case of regression, you update in distribution as a kind of new points, and for the linear regression you don't have it, because I mean, you can reformulate linear regression on the language of the probability distributions, but the Bayesian methods are kind of standing a little bit separately. And what is the autoencoder? In order to talk about the autoencoder, we need to talk about the neural networks. But the very simple idea of the autoencoder, because this is also very famous dimensionality reduction method, is you start from the neural network, which is decreasing the number of neurons, and afterwards reach some point, and it's symmetrically going reverse. So it's like 2 bottles which are connected by the bottlenecks, and that narrow place is exactly called bottleneck. And the idea is that you train that neural network so that whatever the data is on input, the same data is on output. What are you achieving in that case? For example, you know, you on input have, I don't know, 100 values. On output, you need to reproduce the 100 values. But in the bottleneck, you will only have, I don't know, 4 neurons. What does it mean? On practical sense, in order to explain those 100 numbers, you need only 4 numbers in reality. Those 100 numbers, in fact, correspond only to the 4 really independent numbers, while kind of the half of the neural network is going to do, for you to do a very difficult, non-trivial, non-linear transformation. But no one cares, because we know we have another half of the neural network which can reconstruct our data. So as a result, you can use only these values of these 4 neurons and replace it with all the input data. Instead of dealing with, I don't know, 100 inputs, you can have only 4. So, and that's autoencoders, and they're very often used for the various tasks. And they, for example, allow you to find some interesting features in the data, which kind of in the kind of complex graphical data, for example, in images, which you don't even know what they are. Okay, and I think we can kind of the fifth one, kind of the file you can go through yourself because it's very similar. It's about the k-means. The only interesting bit here, which I will comment, but I will not run it, you can run it, is about the kind of, there is this data set moons. And what you can also do with the k-means, you can also do feature maps, or you can do nonlinear transformation. Because if you do k-means on this data set, where this is one class, this is another class, this is the standard data set, which is called moons, you'll get a picture like this, which is not it's supposed to be. But what you can do a feature map or kernel transformation, which is in scikit-learn implemented, and it's called spectral clustering. What you will get, you can get the situation like this. So kind of what you need to really understand about all of that, it's really like a modular structure in kind of in machine learning. Kind of, you can do a linear model, but now you add some features to your kind of whatever learning scenario, which will be nonlinear features, and suddenly your linear model, which could be very nice analyzed with the linear tools, becomes a nonlinear model. And you can stack this thing up on top of each other. So we get this simple idea of the distances for the nearest neighbors. But if you take your data, transform it with some nonlinear transformation, you get the same distances, but now between the features, not between the input data. So between the transform input data. And you can kind of play this game, and the pinnacle of playing all this game is modern neural networks, which kind of very deep and can do quite a bit of things. And those things even kind of, they can do certain things which humans kind of above human level performance, and that we all know by now. Okay. And just to bring it back to the question about the Bayesian linear regression, this is very simple, and this is called Google. So, you know, you just type it in, and there is a Towards Data Science article which explains to you what is the Bayesian linear regression. And I really encourage to do it like this, because as I mentioned, most of the problems which one would end up solving using the machine learning is the problems which somebody else has already struggled with. And so there will be definitely, you know, if your code doesn't work, if it's giving you some error and you don't understand it, there will be definitely someone who have had the same problem, who have seen it, and who have struggled through it. So very likely, if you have really unique errors, that is very interesting. But don't misinform yourself, because you've seen when I was doing a little bit of improvisation, all my errors, whatever I was getting, were pretty standard and typical. So do we have anything else? Okay, I think we could wrap it up, and you could, yes, you can go for the 5th tutorial by yourself, because I think it's not that difficult. And yes, it's just doing the same k-means, but with a little bit of fancy twist. But you know, these fancy twists are absolutely within the realm of what we have. Thank you.